by this internal bias. This is what's causing that variability. Okay, and we're going to test it by estimating the bias using a state space model. So I want to try to estimate how you're feeling. Why are you making these decisions? By estimating that based on just your high-low bets using the state space model. And then I'm going to relate that bias back that I estimated back to the brain. Yeah. No, actually, I'm going to do it a little differently. My signal is behavior. All I'm going to do is observe your high and low bets. From that, I'm going to estimate this dynamic x of t, which is your internal bias. I call it x of t, bad notation, but a signal that's internal, latent, something I can't measure, but that if I estimate it, I can actually predict your bets. Then, once I estimate that signal, I'm going to see where it correlates to how that correlates to brain activity. That's the approach we took here. Yes, and I want to try to figure out if I can estimate that, the dimension and how it evolves and so forth, in such a way that for every person I can predict their bets. Okay? Okay, so I don't think the idea here is, this is more for neuroscience community here. If I have dynamics on 6 cards, I'm basically saying that each of these curves potentially could be modeled as a constant plus some dynamic state variable, latent variable, okay? So the probability that you bet high depends on this internal state as well as the card that you get, okay? And here's how we build that model. So if my betting decision, I'm going to call that Y, is 0 or 1, low or high, 5 or 20. And I'm going to basically say that that's just the probability that you bet high. You're just flipping a coin. Okay? But the bias of the coin P, the probability that you're going to bet high is P, that is a function of 2 things. Your, what we call logical input, the card that you get, okay? As well as this internal bias, X of T, the state that I need to figure out how to estimate. Okay? So if I have U and X, I can compute P and flip the coin, and that's my model for the probability that you bet high on that trial. U and X are a function of T indexed by trial. Okay? And this is just showing that the card plays a role in this U of T, and your internal state depends on your card, the outcome, and feedback, of course, whether you've been winning or whether you've been losing. So that's where the memory is in the system. Okay? Specifically, here's what we do. We bet probability that you bet high, or $20. We're going to denote that as P on trial T, PT, okay? And we're going to just use a simple logistic regression, okay? We're going to say the log of the odds on trial T is some combination of the internal state, maybe just a constant bias or baseline of betting high, as well as the card that you get, okay? So in particular, we're going to look at the expected outcome conditioned on the card as your U of T input, okay? So this is internal bias, this is logic, and this could be sort of the baseline, how risk averse you are at baseline, okay? So that's sort of my output model for my output, instantaneous output equation, yeah. 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 Yeah, so I'm going to get there, but I don't know I don't know X, I don't know C, D naught, and D1 so far. The SEEG is not in this model yet. I'm going to show you how we connect it to the SEEG, okay? See the neural activity. So first, the approach we took, again, it's not the only approach, is we wanted to be able to predict and explain behavior, all these also variability of your bets, and then once we feel like we can predict well, because we believe this internal bias is going to be highly predictive, then we're going to relate that bias back to the brain and see what happens. Yeah. Yeah.
I'm going to pay so that I can maximize my profit.
Right. Right.
What's hidden in there is, one is how is my sort of risk changing?
Yes.
And so forth.
Right.
who's they?
Right. So good. So what he's saying, I think if I were to repeat what I think you're saying, is at the end of the day, maybe I'm always interested in maximizing expected reward. But over time, the odds of winning on a 2 or winning on a 4 actually are not 0.2 anymore. They actually might change in my mind depending on how I feel and so forth. But at the end of the day, I still have odds. I can still compute the expected reward and play optimally in that sense, right? But I'm saying I agree with you. All I'm saying is that your perception of the odds change with X.
Yeah. So what
Is
I'm
that,
thinking is that if you formulate the problem, then
yeah, your beliefs. Yeah. Yes. Yes. Yes.
And that becomes my bias that it has some sort of
Yes.
based on the happening.
This is it. Yeah, that's exactly right. So the X is like your belief, if you will. It's going to play a role in the belief. So right, so I gave you the output equation. Now this is the state evolution equation. So obviously I don't know X, it's latent, but I need to, construct some model for how I think it evolves over trial, right? And so I'm going to show you one evolution equation. We didn't get there easily. Actually, we did a lot of data exploration to figure out what could possibly be playing a role in this bias. So here's the idea. So let's just think X of t, let's just pretend it's how you feel on trial t, okay, just to get through this equation. So on trial t plus 1, how I feel depends on how I felt in the previous trial. So there's some memory. If I felt good, I might still feel good, okay, in the next trial. It depends on the previous card value. If I just got a 10 card, I might feel really good now, right? And it also depends on performance. Okay, so this is actually risk as quantified by the variance of the reward conditioned on the card. So it's the standard deviation, if you will, times a prediction error. So in the previous trial, I had an expectation of what my reward was, and I have an actual reward. So for example, if I took a very risky bet and I won unexpectedly, then that might make me feel really good. And vice versa, if I lost on something I thought I should have won, maybe it'll make me feel bad. So what we're saying in the state evolution equation is the state at time t plus 1 depends on the state at the previous time, the card value that I got, as well as my performance. Okay? And so now, once I have this particular evolution equation, I need to just estimate A, B1, and B2, the parameters. And this is just additive Gaussian noise. And I estimate the variance. So it's scalar. Very simple. We just started with a simple scalar model. Yeah, so that's exactly right. So it's kind of like getting at, I think, what Munzer was saying, which is you have this belief. It gives you notions of priors on probabilities of given cards, and what you're trying to do is maximize profit. And this is what we believe is how you're updating your priors. Yeah.
Maybe a different model can be thought you feeling good, feeling high, bad,
right.
Yeah.
Yeah. We did so many things, actually, but remember what I'm going to be after is I want to see if I can predict your behavior with a model, okay? So that's going to be my validation, yeah.
So does the model capture loss aversion?
Loss aversion, yeah, you're going to see it. So I'm going to show you. So we're going to build this model subject by subject, and there are going to be some people that display more or less severe loss aversion and others that don't. You're going to see this come out of the model itself. Yeah. Yeah.
I think that's sort of what happens in the down.
Yeah.
Energy goes away, and that's what the sort of the moment irrationality. That's the content.
Right. Right.
And so I think that in some ways really sort of involved in that outcome.
Right, and it's different for person to person. It is. There are people. Yeah, there are people, and I'll show you. But there are people that have actually exhibit what's called gambler's fallacy. So, which means if they just had a winning streak, they actually think, "Oh, I'm not going to win now. I just won 5 times. The chance of me winning again goes down." It's ludicrous. Of course, it doesn't go down. The odds of the game have stayed the same. But you have that psyche, right? And there's the other side, the opposite, which is hot-handedness. So they study this in psychiatry very well. Hot-handedness means you just won 5 times in a row. You think, I've got a hot hand. I'm going to win again. I'm going to bet high on that too, right? So we see, we can actually quantify that with our model. You'll see it come right out of the model. Yeah. Yeah. Yeah, you're going to see this. So I'm going to get at these gambler fallacy people and the hot-headed through these B's. Yeah, that's exactly right. Yeah. So reward, sorry. So this is expected reward conditioned on the card, okay, and the outcome, and then the actual reward. Expected reward minus reward. Vice versa. Yeah. Okay, so here's my state space model. So we estimate that, sorry, I need to push on this, through standard maximum likelihood estimation procedures. Since I don't have the states, I need to do like an iterative EM algorithm. I'm going to skip that. Here are some of the results, okay? So this just so I orient you on how we display the models. So here's an example of a model for one subject. Red is high bet, blue is low bet. The y-axis is P of t, my probability of betting high on any trial T, and I'm plotting that versus bias, the estimated bias for that subject, okay? And what you can see here, and what this is a model for the 6 cards, okay? So this is a person that actually bet low sometimes on 6 cards, which are the blue trials, and red circles are when this person bet high. And one thing you can see here is when the bias signal was negative, this person was more likely to bet low on the 6 card, but when the bias was positive, you see more reds. Okay, and the estimated bias for this patient over trials was this green curve. So this is the mean. So x of t turns out to be Gaussian. So it has a mean and a variance. So shaded regions are plus or minus 2 standard deviations. So the green is the mean, and look what you can see. So you see these peaks happening when they're positive peaks. You see the circles, by the way, are 6 card trials. When you see positive peaks next, you see that most of the time you predict that they bet high on the 6 card. When you see negative peaks, they're mostly associated with betting low on the 6 cards. But we estimate X across the whole session, okay? It just seems to be the case for this patient that the bias doesn't seem to play a role when you get a 2-4 or an 8-10 for this subject, okay? So that's why you see the rest of the model, these are the different card values. The model for the 2 card almost always bet low on 2 and 4, and this person almost always bet high on 8 and 10, was only dynamic on the 6 card. So we did this model for every patient, patient by patient, and we saw a spectrum of gamblers, right? So people who were very logical, really not affected by a bias, to being dynamic on all cards, constantly changing their strategy and their bets on all the cards, okay? And so the question is, it looks just qualitatively that, you know, when the bias is negative, they tend to bet low, and when the bias is positive, they take more risks. So this bias seems to be related to the risk that they take, because betting high is always higher variance, higher risk. When we did model validation, we said, okay, for every subject, if I were to compare my model with the state versus without the state, okay, so if I'm going to build a model just based on your probability of betting, just as a function of your cards, nothing else. That's the static model. And now I'm going to compare that to how well we predict by incorporating the state, okay? And you can see that if you just, for example, look at prediction error, most of the time, including the state, helps predict the behavior of that subject. Yeah, so it's hard in this because we're limited in data. We only have about 120 trials, 150 trials on a patient. So we didn't do training and testing, but we did bootstrap, and I'm not showing results here, but to try to get at, does the state actually help predict? We basically do bootstrapping procedures and cross-validation on the whole set to make sure that we get stability in terms of performance. But we're restricted, we're limited by the data sample to do stuff like that here. Yes. So I think this gets at what you're saying. I'm not sure, but ask me again if I don't hit. So once we looked at the models, once we built these models and it seems to be predictive of behavior, we tried to look at the parameters to see, are there different gamblers, right? So this is to your point here. So if you look at just the Bs in the state of evolution equation, B1 versus B2, you see two clusters essentially. These guys here have the hot-handed fallacy, meaning if they just have a bunch of wins and they take these risks and they win, they keep thinking they're going to win, and these are the opposites. I think we had a question on there. And you get that comes right out of the model parameters. Is that what you were getting at? Or yes. You mean just sort of how the accumulation of winnings over time for each subject? Is that what you mean? Yeah. Oh, we didn't do any sort of rigorous analysis of just saying if you, for a given strategy, what's this distribution of your winnings at the end? We haven't done it. You could do that for this game. If you wanted to, you could run that test and see what things look like. Is it a proxy for, look, so yeah, so this is, you see this component in a lot of reinforcement learning models where they do try to correlate sort of the learning to dopaminergic activity in the brain. Yes, it's very similar to that. They do have this prediction error, reward prediction error in their equations, but they don't multiply it by this risk. It's a little different, but yeah. Now, I want to get to the end. I'm almost done. Okay, so then once we figure out the X of t, this is where we got some interesting findings. X of t for every patient, we said, okay, X of t is modulating for every patient. I want to see, as X of t changes, are there brain regions that have activity that change with it, either positively correlated or negatively correlated. And given the time, I think what I'm going to do is probably get straight to, I'll give you an idea of how we did the analysis, and then I'm going to go straight to the result and close, okay? So the way we did this is, remember we have recordings from each of these contexts. So you get the signal coming from each brain region, each patient, and you're recording this over the entire session. Here are the different trials when they occur. And let's say I split all the trials between all the trials where you had a low bias value versus a high bias value. Remember, I estimated the bias. But that's low X of t, high X of t. So for every trial, I can say, is my X of t low for that patient or high? Now I'm going to create these two groups. Okay? Then what I do is I take the neural activity in a window, let's say right after you saw your card, and I'm going to compute a spectrogram in that window from your neural activity. So this is the time. This might be when the computer card was shown. So I time lock the neural activity to that event. I look a little bit before, a little bit after. This is time, and this is frequency, and I can compute the spectrogram. Okay? And I can do this for all the low trials. So I collect all the spectrogram for low bias trials. I collect all the spectrograms for high bias trials, for example. And then I ask the question, is there any time frequency cluster that differs between the two conditions? Okay? Does that make sense? Because if there is a cluster in time and frequency that differs between low and high trials, then that brain region is encoding bias. Okay? So conceptually, that's what we do. Okay? And we use what's called a non-parametric statistical test with clusters. I'm not going to go into the details. I'm happy to talk about it offline because I feel bad I'm taking a lot of time here. But basically, here's an example where, let's say these are win trials or loss trials, and I have a bunch of these spectrograms and many of these. I can perform a test that tries to account for multiple comparisons, dependencies in the time and frequency, and I'll get a cluster that says, okay, this is the region in frequency and time that differs between the two conditions. And in this way, for every recording, every brain region, I can say, do you encode bias or not? And are you positively encoding the correlated with bias or negatively correlated with bias? Okay? When we do that, here's what we see. I'm going to skip to this. Sorry. Okay, so whoops. So let's just focus on the top picture. Top left corner here, okay? Okay, so this is just a simple MRI scan. The interpretation of this is if you see a red color anywhere here, it means that region not only encodes bias based on our analysis, but it is negatively correlated to bias. Okay? And if it's green, it's positively correlated to bias. And this is the trial, what happens throughout the trial. So when you see your card, when you make your bet, when you see the computer card and you get your reward, I can ask, are you encoding bias or not? And are you negatively correlated or positively correlated? These are just two different slices, viewpoints of the brain. What do you see here? Any trend? Somebody's saying there seems to be some lateralization going on, that on the most of the time, the left side of the brain, if it's encoding bias, is negatively correlated, which means that the activity is high when your exit is low. And the other one is high activity when your bias is high. What's the frequency band at which this is happening? Okay, remember the cluster test was talking about a frequency. Well, it turns out if you look at what frequency this region is encoding the bias, for example, you'll see we looked at different frequency bands. This is high frequency. High gamma is like 150 to 200 hertz. Delta is low. And most of the time, bias is encoded in high gamma. Actually, people have shown that this high gamma activity correlates to spiking activity. So there seems to be a correlation between when neurons are firing and high gamma from the C signal, okay? So it looks like lateralization high gamma. So that's exactly when we look at the number of regions in left versus right brain that are encoding bias, you see in the high gamma a strong push-pull effect, right? If I have high activity in the gamma band in right brain, that correlates to high bias, which means you're going to bet high more likely. And if it's left, you're going to bias is low, and you're going to probably bet low. This push-pull phenomena. So this is what happened at the end. So as these patients were gambling, if I have high activity on the right side of the brain, I'm actually more likely to make that high bet. And if I have high activity in the left, I'm more likely to make a conservative bet. And this was nice because these regions that were encoding bias were everywhere. It was not just the front of the brain, which most of the neuroscience community has focused on. Actually, it was starting in deeper structures that have to do with emotion and language and things that are pushing you into one direction or the other. So I'm going to skip. I had a movie that's just showing the population activity. The last thing is we wanted to say, okay, if we know we're encoding bias, can I actually decode? Meaning, can I just look at your neural activity and estimate your bias? So going in the other direction. So we had very limited data, but we wanted to try it out. And so the bias signal for this is an example of a X of t is the red, as estimated from our model. And blue is our prediction of bias just by looking at the neural activity. Okay, so it looks like you can decode. So I'm not going to conclude there because I want to be done. But I wanted to say, so, Munzer said that, I work a lot with clinicians. This study absolutely could not have happened without a big team involved, right? So we needed the neurosurgeon on board that's going to let us, who put the electrodes in the brain, that's going to let us work with his patients. We had John Gale, a PhD electrophysiologist, who actually did the experiments at the Cleveland Clinic. I had my postdoc, who's now professor at the University of Liège, who did all the data analysis. And just to give you an appreciation, even though the model is simplistic, scalar state, it took years to do this, okay? And just imagine you get signals, many, many signals from individual, from the same structure across patients. So I've got hundreds of signals over 30 minutes of data, hundreds of signals from all these different brain regions, and we needed to make sure, and then you have to figure out, okay, what are they encoding and so forth. To your question, can I do something else to change their behavior? So although the videos don't work here, there's two things we talked about in terms of testing causality. So there's nothing causal. These are all correlation analysis. So one thing we wanted to do is we thought, okay, let's rig the deck. Let's make somebody win more, have more of a winning streak or losing streak, and see if we can change the way they bet, okay, affect them. Another way is actually to stimulate some of these regions that we found were encoding bias, right? We know that if the right side of the brain has high frequency activity, they're more likely to take a risk. So why don't I just stimulate and generate that fast activity and make people risk takers? And that could then demonstrate causality. So those are some of the directions we're going in today. Yeah. If you had 10, 15 electrodes drilled in your head, do you think you want to learn probability? I don't think so. A table. Yeah, so we could try to make them more rational players. If you want to just, look, they're looking at the table, it reminds them the odds haven't changed, and they just do the same thing every time. It's boring. I mean, if they're doing the same thing every time, I'm not going to see any modulation in the brain, right? Okay. So yeah, we did let them play this game before they started. So we do have sort of a training session, a practice session, if you will, before they do this. Yeah.
Yourself changed the game was not as described.
Yes.
In the sense that you gave some people a winning.
We didn't do anything. The deck was, no, I'm saying that's what we can do in the future. So,
okay, so there is the possibility that the experimenter is doing that and not
yes.
So,
yeah.
So, I mean,
right.
Human beings have evolved in a world where there is no instruction manual. Discover the world
by navigating. Yeah.
So, I mean, it's not clear that the people who are more accurately were doing wrong.
Oh, I'm not saying they're doing anything wrong. Yeah.
Caught on to something in the system.
Right.
So to say that irrational is something.
So I don't like to use the word irrational. In fact, we didn't use it anywhere in our paper because exactly this type of criticism we'd get from reviewers. So we don't say that. We just say you have a bias. It can be positive or negative, and when your bias is positive, it makes you take more risks. And this is how you play the game versus how he plays the game. Yeah. Yes. Well, it's not even low. It's actually highly distributed, right? It was throughout the entire brain, actually. It was right hemisphere, left hemisphere. What we were able to cover is what we saw. But some of you are interested in evolutionary, right? So one thing is why this lateralization push-pull. Well, actually, it's not the first system that has this push-pull mechanism, right? We have this approach avoidance network in the brain. That's key for survival. You need to know when you're going to approach an object versus when you need to get away from it.